Well, on to our next presenter. Liat Margolis is professor and director of the Daniels Faculty's GRIT Lab, and that does not mean she studies persistence or sandy particles. GRIT stands for Green Roof Innovation Testing. So Liat is an expert on the interaction of nature and the urban environment. Tonight she's going to talk about what cities can do to fight climate change. And the answer is we literally open cracks in the concrete and asphalt and glass and steel and let Mother Nature in. Please welcome Liat Margolis.
Thank you. The day this photo was taken, 126 millimeters of rainfall dumped on the city of Toronto in about a 2-hour period. And just to put it in perspective, this is equal to more than the city typically gets in the entire month of July. So we had public transit completely inundated by severe flooding, thousands of commuters stranded, basements flooded, power outages, and over 1 billion liters of sewage surged through the streets of Toronto and its harbor. As Toronto star Christopher Hume wrote at the time, we face a double whammy of disaster. Not only are our city's aging infrastructure unable to cope with the load, but the load has grown heavier due to climate change. Climate change certainly raises difficult and important questions around the future of our cities. And the question is, what can we do to mitigate the impact of this so-called new normal of extreme climate events? And what kind of approaches and solutions could we have that not only lessen the impact, but also improve the overall environmental, social, and economic prosperity of our communities? Now, I'm going to make the pitch that we must look at our city as a landscape. And then I'll argue for the fact that living green infrastructure is absolutely crucial for not only climate resilience, but also for the overall sustainability of our communities. So what is green living infrastructure? Green infrastructure solutions and technologies range in scale and type from interconnected networks of green spaces to street trees to green roofing. Green infrastructure includes both natural and constructed technologies or landscapes. And the critical point is its collective impact on our urban region. In other words, we must think of them as an integral part of city planning and to actually implement a diverse set of solutions across the city at multiple scales. Two examples from the recent reconstruction of the Toronto waterfront showcase this kind of thinking. This is the Biofiltration Park at Sherbourne Common, which is designed to filter and treat stormwater water from all the urban pollutants before it hits the lake. This is a suspended pavement and tree system which is designed to capture 90% of the stormwater from the waterfront before it enters the lake. And this integrated design is then intended to not only manage stormwater and filter the water, but also provide with the kind of cooling and shading, the kind of increased habitat and social benefits that are included in this particular design. In other words, the second critical point about green infrastructure is that its advantage, unlike a traditional or conventional stormwater pipe system, is that it's inherently multifunctional. Now, the idea that landscape systems have the capacity to regulate climate, control flooding, increase habitat, improve air quality, and filter pollutants from urban water and soil is not new. New York's Central Park, designed by landscape architect and public health official Frederick Law Olmsted in the late 1800s, was conceived as a green lung for the industrial city. The Emerald Necklace in Boston was envisioned as a green spine around which the city would evolve. Parts of it were designed and engineered to filter and treat urban sewage or urban effluent through constructed wetlands before it flowed into the Charles River. But we also experience bouts of landscape amnesia, where we pave over our rivers, we cut down our forests, and we build into floodplains. This image is of Garrison Creek, which, along with many lost rivers in Toronto, was buried and piped. And it took the catastrophic storm of 1954 during Hurricane Hazel to have Torontonians recognize that the natural heritage of the ravines is the underlying core structure of our city, crucial for its function and prosperity. Since 1954, the Toronto Region Conservation Authority, or TRCA, has the legislative power to protect and restore this valuable natural heritage. And another success story of green infrastructure at the regional scale is the Ontario Greenbelt. Spanning over 7,000 kilometers squared, this is one of the largest green belts in the world. Its forest cover offsets 27 million cars worth of greenhouse gas emissions. It also anchors agriculture, recreation, and tourism industry, contributing to $90 billion in annual revenue. And it also contributes to over $2.5 billion in ecosystem services, such as aquifer recharge and flood control. Now, one of the most significant changes in recent times is the actual quantification of environmental performance. Scientific research is amassing tremendous amount of data, which is allowing us to then evaluate the effectiveness of these green solutions and develop evidence-based policies and investments. For instance, TD Bank valued Toronto's urban forests at $80 million annually in ecosystem services, ranging from flood control to air quality to thermal cooling. Increasingly, municipal and provincial or regional governments are expanding their definition of infrastructure to include green infrastructure. And the City of Toronto is among those who are leading the pack. For instance, in 2009, the City of Toronto was the first in North America to legislate a green roof bylaw, which is part of its suite of solutions to address its urban water management, energy conservation, and biodiversity targets. And it's precisely that bylaw that motivated our research group, the Grit Lab, to form, and in order to evaluate how effective are current green roof practices relative to the city's objectives. So here's our current lab, which is located on top of our now former faculty building at 230 College Street here at the University of Toronto. This is a multidisciplinary research initiatives which involves the engineering department, civil engineering, mechanical engineering, ecology, biology, landscape architecture, and building science. And here we have 3 research areas that we're focusing on. One is green roof research, green facades, and green roof integrated solar voltaics. Our approach is to essentially construct test beds of green technologies, a variety of different green building practices, and study them in real time via sensor technologies. In a way, this principle to convert many of our buildings on campus as this kind of living lab to test green building technologies. To date, we have in this lab over 500 sensors that record solar radiation, wind, humidity, soil moisture, drainage, temperature, and energy output every 5 minutes. We can then calculate what the kind of nature of a rain event in terms of its volume, frequency, duration, and then relate that and compare that to the performance of each green roofs, and then communicate that back to industry and policymakers with respect to what standards work best. We can then look at that water cycle and relate that to the thermal cooling and determine whether the localized cooling underneath the panels actually optimize energy production. We can look at whether the different material configurations impact plant growth, evapotranspiration, and the overall performance of the green roof. We can also look at what plant selection, how that impacts patterns of pollinator or foraging patterns of pollinators and so on. In other words, the whole intent is to essentially ask ourselves, how green are green roof technologies, and what are the most effective guidelines for constructions? We can then recalibrate their configurations to yield better performance and communicate that to policymakers and design practitioners. In other words, we're looking at a kind of approach of a green roofs 2.0, if you will. Now let's think back to that storm of 2013. The good news is that green roofs, regardless of their configuration, material configuration, capture over 90% of the total water volume of the peak of the storm. And this is absolutely significant in terms of helping the city cope with the kind of heavy loads of the storms that we're seeing. But we're also finding, in our next research agenda for One Spadina, what we're going to be looking at is actually reusing the rainwater that's collected in an underground cistern in order to further control flooding, also improve the water quality from all the surface runoff, and conserve water. And this will be our next research agenda. We're looking at all sorts of different practices in the industry. For instance, despite the fact that the green roofing industry and the solar industries usually compete for the same roof surface in construction and rarely combine the two technologies together, what we're finding is the two technologies are actually have a lower life cycle cost in terms of energy emissions or energy consumption and carbon emissions. Lower than the two systems installed separately. We're also finding that green facades contribute to the cooling of building envelopes and decreasing energy demand for cooling in the summertime. But what we're finding is that some of the kind of decisions around material choices do make a difference. In other words, no green roofs are created equal, and that material choices make a huge difference in terms of their capacity for stormwater retention, the kind of effects on biodiversity and pollinators, thermal cooling and whatnot. For instance, some of the beds that we have looked at end up in complete plant die-off where their surface temperature is equal to or higher than a conventional rooftop, making the trade-offs in terms of energy and emissions unjustified. So in other words, material choices and site and context matter. And as we make strides in policy and building practices, research is really key to develop regionally specific metrics and guidelines that could improve the kind of environmental performance with these technologies. For instance, one of the findings that we've had is that the industry favorite plant selection attracts non-native pollinators, where the more biodiverse grasses and flowering plants attract native pollinators. Now, this could have immense implications on a regional scale in terms of pollination and ecology. So these decisions, even though they might seem very small and very minute, when aggregated together as a kind of the concept of this collective impact, could have maybe an undesirable or a negative impact on an ecological scale. I'd say in summary, living infrastructure, in my view, is really critical to the way that we're developing cities, particularly in light of a changing climate. They're absolutely crucial to the function, resilience, and prosperity of our communities. We should really think about living infrastructure or infrastructure beyond just roads and buildings, and that our natural heritage is an essential part of our sort of the foundation of this city. So in short, I would leave you with just one thought in saying that the living infrastructure is the architecture of the future. Thank you.
Thank you, Liat. I love that idea of the green infrastructure, the living infrastructure, having not only this engineering function, but having multifunctionality and essentially a social element baked right into it. It's fascinating.